Imagine trusting a billion-dollar supercomputer to predict a lethal heat wave that's just barreling toward your city, only to find out its brain is permanently stuck in the winter of 1998.
Right. It's wild. It is the ultimate technological paradox we're facing right now.
Because we are currently building the most advanced, lightning-fast artificial intelligence in human history to forecast our weather. And we just assume this technology is relentlessly futuristic, operating entirely on the bleeding edge of tomorrow.
Yeah, you would think so.
Yeah.
But there's a massive glitch in the matrix here. The very AI systems we are starting to rely on to navigate a rapidly changing planet are, well, they're essentially living in the past.
Right.
Structurally, their programming really only allows them to look backward.
Welcome to today's deep dive. We are exploring a fascinating 2026 paper by researchers Jacob Landsberg and Elizabeth Barnes. They're at Colorado State and Boston University,
And the paper's titled Forecasting the Future with Yesterday's Climate.
which is just a great title. Our mission for you today is to unpack exactly why our cutting-edge AI weather models have this bizarre time machine problem. We're going to look at the underlying mechanics of how these models process data, what happens when they try to predict modern extreme heat, and why simply, I don't know, adding carbon dioxide data doesn't fix the glitch.
And of course, how scientists are trying to correct these systems before we bet our critical infrastructure on them. Because to really grasp the scale of this problem, we first have to understand the massive paradigm shift that's happened in forecasting over just the last 5 years.
Okay, let's unpack this, because the mechanics here are crucial.
Right, so for decades, traditional weather and climate prediction relied on what we call dynamical models. These are governed entirely by the laws of physics.
Like actual math equations.
Exactly. You take the Navier-Stokes equations for fluid dynamics, you apply the laws of thermodynamics, and you code them into a massive supercomputer. The computer divides the Earth's atmosphere into a 3D grid and just painstakingly calculates how air, moisture, and heat move from one grid box to the next.
So you are explicitly teaching the computer the fundamental rules of the universe. You're saying, here is how a gas expands when it gets warm. Now apply that rule to the whole planet.
Yeah, that's spot on. But doing that requires an unbelievable amount of computing power. Running those physical calculations for every point on Earth at every altitude, minute by minute, it is incredibly slow and wildly expensive.
I can imagine. So that's where the AI comes in, right?
Exactly. Recently, a new generation of fully data-driven AI models has emerged. We're talking about models like ForecastNet, which was designed by NVIDIA, or Pangu Weather by Huawei.
And these are different.
Completely different. These neural networks do not use physics equations. They don't know the laws of thermodynamics at all. Instead, developers just feed them massive data sets of historical weather conditions spanning decades.
Wow, okay. So the AI analyzes millions of past weather maps and learns the complex statistical relationships and patterns directly from that data. It's basically learning by pure observation.
Yes, it looks at a million Tuesdays from the past to guess what next Tuesday will look like. And because it's just pattern matching, instead of doing heavy physics math, it runs remarkably fast.
Right, you can run hundreds of AI simulations in the time it takes a traditional supercomputer to crunch just one physics-based forecast.
The efficiency gains are revolutionary. I mean, in terms of day-to-day accuracy, they are matching and sometimes beating the traditional models. But, and here's the catch, this is exactly where the time machine glitch introduced in the Landsberg and Barnes paper comes into play.
Here we go.
Because these models learn entirely by example, they face a fundamental hurdle. The climate they trained on, it no longer exists.
Okay, I want to challenge that for a second, because if you're listening to this, you might be thinking, wait, if NVIDIA and Huawei are pouring billions of dollars into these models and they know the planet is warming, why don't they just train the AI exclusively on weather data from the last 5 years?
Right, why use data from decades ago at all? It is the logical question, totally. But it hits the wall of how deep learning actually functions. These are massive neural networks with billions of parameters. To tune those parameters so the AI can accurately recognize a hurricane or cold front, it requires an astronomical volume of training data.
Oh, so 5 years just isn't enough.
Not even close. 5 years of weather data simply isn't enough to teach a model the full complexity of the Earth's atmosphere. You have to feed it the entire high-quality historical record, which typically goes back to 1979, when the satellite era really took off.
I see. So you need volume. You have to feed it the 80s, the 90s, and the 2000s just to give it enough examples of how clouds form and jet streams move.
Precisely. And mathematically, when you train a model on a data set spanning from 1979 to the present, the statistical center of mass of that data lands right around the late 1990s.
That makes sense.
So the AI essentially develops its baseline understanding of what normal weather looks like based on the climate of like 1997 or 1998.
Which brings up a way to visualize this. It's kind of like smartphone autocorrect, right?
Oh, yeah, that's a great way to put it.
Like, your phone guesses the next word you're going to type based on a massive history of everything you've ever typed before. If you constantly text your friends about ducks at the pond, the moment you type DUC, it predicts duck.
Right, exactly.
The AI is doing the exact same thing with atmospheric pressure and temperature. But if you have never typed the word heat wave in your life, your phone isn't going to suggest it.
That autocorrect analogy translates perfectly to the researchers' findings. To test this blind spot, Landsberg and Barnes focused on a very specific slice of weather. They looked at boreal winterland temperatures.
Okay, meaning wintertime in the northern hemisphere over land masses.
Yes, excluding Greenland. And they chose this because, historically, winter temperatures in the northern hemisphere over land have been warming much more rapidly than the global average. This is the ultimate stress test.
So if an AI is going to crack under the pressure of a changing climate, this is where the fractures will appear.
Exactly. So they took these models, whose brains are anchored in the late 90s, and asked them to predict the weather for a modern period, specifically 2020 through 2025.
What happens when a 1998 brain tries to forecast a Tuesday in 2024?
What's fascinating here is the absolute universality of the flaw. They tested two weather models, ForecastNet and Pangu, and every single prediction they produced had a distinct cold bias.
Every single one.
Every single one. When the researchers mapped out the temperatures the AI was predicting for the 2020s, the forecast didn't look like modern weather at all. They perfectly resembled the actual measured climate of 15 to 20 years earlier.
Wow. And looking at the data in the paper, it shows that in certain regions, particularly the eastern United States, the AI's predictions were lagging by 20 to 30 years.
Yeah, 20 to 30 years. It was handing us forecasts that looked like the mid-1990s.
That is a massively populated area relying on data that is functionally decades out of date.
It really is.
Yeah.
And the researchers actually highlighted a brilliant irony to underscore how deep this problem goes. They compared the multi-million-dollar AI against something called a 9-day persistence forecast.
Okay, what is that?
A persistence forecast is the most basic prediction method imaginable. You literally just look at the temperature today and say, I predict the weather 9 days from now will be exactly the same as it is today. Zero math, zero machine learning.
And the paper shows that this zero math persistence forecast actually predicted modern average temperatures better than the highly sophisticated neural networks.
It did. Because a persistence forecast uses today's data as its starting point, so it implicitly captures today's warmer baseline. The AI, despite its incredible architecture and billions of parameters, is just blind to the overarching warming trend.
It is mathematically shackled to the historical patterns it memorized.
Exactly.
But here's where it gets really interesting. Being slightly wrong on an average Tuesday is one thing. But if these models are stuck in the 90s, what happens when a modern, unprecedented extreme event hits? Let's talk about heat waves.
Yeah, so when we shift from looking at average everyday temperatures to looking at the extremes, the far tails of the temperature distribution, the failures of ForecastNet and Pangu become stark.
They get worse.
Much worse. Their biggest errors aren't happening on mild days. They fail spectacularly on the hottest days. When analyzing the top 10% hottest temperatures in that 2020 to 2025 period, ForecastNet was almost a full degree Kelvin, colder than reality. It was 0.91 K off, to be exact.
To give that everyday context for you listening, a change of 1 degree Kelvin is exactly the same magnitude as a change of 1 degree Celsius, which is nearly 2 degrees Fahrenheit. That might sound small if you're just walking outside, but if you're predicting a regional average during a record-breaking heat wave, underestimating the temperature by a full degree Celsius is a massive failure.
It's huge.
But wait, you mentioned the hot days. How did the models handle the coldest days of the 2020s?
This is the critical mechanism. On the top 10% coldest days, the AI was highly accurate. Pangu was even slightly too warm by 0.12 K. Yeah, the models can predict modern freezing temperatures just fine, but when a massive heat wave rolls in, they essentially pull the prediction downward, forecasting a cooler day than what actually transpires.
Okay, let's dig into the why here. Why does the AI panic and predict cooler temperatures when it sees the atmospheric setup for a modern heat wave?
It all comes down to the numbers game of the training data. In the model's historical dataset, There is literally 2 to 3 times more data representing what we would consider a modern cold extreme than a modern hot extreme.
Because the baseline climate was cooler in the 70s, 80s, and 90s?
Right. What we consider an extreme cold day in 2024 was a much more common occurrence 30 years ago. So the AI statistical bucket for cold weather is just overflowing with examples.
But its bucket for a 2024-style heat wave is nearly empty. It looks at the precursor weather patterns, the high-pressure dome forming, the soil moisture dropping, and says, I have never seen it get that hot from these conditions in my entire 40-year memory. Statistically, it's more likely to be a standard warm day. So it violently regresses the forecast back toward the historical average.
Yep. It simply lacks the vocabulary for unprecedented heat. It is just regressing to the mean of its training set.
Okay, so there is an obvious engineering solution that jumps out here. If the weather models are failing because they don't know the climate is changing, why can't developers just explicitly program a warming rule into the algorithm? Like, why not just feed carbon dioxide data directly into the system so it knows the baseline is shifting?
Right. And the researchers explored that exact premise by looking at a model called ACE2. ACE2 is an AI climate model built by the Allen Institute for AI.
Okay.
It uses an architecture very similar to the weather models we just discussed, but it is explicitly designed for long-term climate prediction. And to help it understand those long-term trends, the developers actually fed it specific historical CO2 forcing data.
CO2 forcing data, meaning it actually knows the concentration of greenhouse gases in the atmosphere, and it knows those gases trap heat. It has the trend line.
It has a trend line.
Yeah.
And the theory is that if the AI knows CO2 is rising, it should adjust its temperature predictions upward, right? Effectively fixing the time machine glitch.
Right. Did it work?
Well, the twist here is profound. Even with that explicit CO2 data, ACE2 still exhibits a significant global cold bias. When trying to predict a period slightly outside its core training range, it was globally too cold by 0.35 K.
Wait, really?
Yeah, but the nature of its failure is the exact opposite of the weather models.
Opposite how?
Okay, so ForecastNet and Pangu failed hardest when trying to predict the hottest days, right?
Hmm.
ACE2 fails hardest when trying to predict the coldest temperatures. It has a massive cold bias in the cold tail of the distribution.
Meaning it predicts winters that are much colder than they actually are. Wait, I need to wrap my head around the logic there. If you give an AI data showing that greenhouse gases are rising and the planet is warming, why does it respond by predicting winters that are too cold?
If we connect this to the bigger picture of atmospheric physics, it actually makes perfect sense. We have to look at the historical reality of how climate change actually manifests.
Okay.
Over the 20th century, the climate hasn't warmed evenly. It's not just a uniform 1-degree shift across the entire globe. Historically, winters have warmed much faster than summers. Nighttime temperatures have warmed faster than daytime temperatures.
Oh, wow. So the floor is rising faster than the ceiling.
Yes, exactly. The absolute coldest days of the year have warmed significantly faster than the hottest days, particularly over land masses like North America, Europe, and Russia.
Why is that?
There are physical reasons for this, like the ice albedo feedback. As sea ice and snow cover melt earlier in the season, the dark ocean and land absorb more heat, which is then released during the winter, disproportionately warming the coldest months.
Okay, so how does ACE2's neural network interpret that? I mean, it was trained on data mostly from 1940 to 1995, right?
Right.
During that half century, it learned the deep, complex spatial patterns of the atmosphere. It learned the exact shape and behavior of a winter storm in the American Midwest or a Siberian cold snap.
And it learned those specific physical patterns during a time when those cold extremes were significantly colder than they are today. So ACE2's bias perfectly mirrors the real-world asymmetry of climate change. It fails most dramatically in the exact regions, the exact seasons, and the exact temperature extremes where historical warming has been the most aggressive.
That really highlights the limitation of just throwing a CO2 trend line at the problem. Giving the AI a carbon dioxide input isn't enough to overwrite the deeply ingrained structural assumptions it learned from decades of outdated weather maps.
No, it's not.
It mathematically understands that the world is getting warmer on average, but its underlying pattern matching still thinks a winter storm in Chicago behaves exactly the way it did in 1975. The specific dynamics of the past are just anchoring its logic.
The structural pattern matching is simply too strong. A global CO2 forcing cannot completely erase the local artifacts of the training set.
So let's bring this into the real world. So what does this all mean? Why does it matter to you, the listener, if a supercomputer is off by a fraction of a degree in predicting the extremes of a season?
It matters deeply because we rely on these models for the backbone of our critical infrastructure. We use seasonal forecasts to manage water reservoirs,
Hmm.
plan agricultural planting cycles, and most urgently, we use them to prepare city power grids for extreme weather.
Right. Think about managing the power grid in Texas or California. The grid operators need to know exactly how hot a looming July week is going to get so they can accurately predict air conditioning loads. If your forecast model systematically underestimates the peak of a heat wave by a full degree Celsius because its brain is stuck in 1998, you aren't going to secure enough reserve power.
And that fraction of a degree
Hmm.
represents the very real difference between a stressed power grid and catastrophic rolling blackouts. These new AI models are incredibly attractive to energy companies and governments because they're so fast and inexpensive to run.
Yeah, they're cheap.
But if they are fundamentally blind to unprecedented extremes, they could leave us dangerously unprepared. We risk walking into modern crises armed with forecasts from the 1990s.
Yikes.
The danger is that because these AI models are so incredibly accurate on an average day, we might develop a false sense of security and trust them blindly when the extremes hit.
So, are scientists suggesting we just scrap the AI and go back to the massive, slow, physics-based supercomputers?
Oh, not at all. The potential of AI forecasting is too massive to abandon. Instead, researchers are actively engineering solutions to break the time machine effect.
Oh.
One major approach is augmenting the training data. Instead of really feeding the AI historical observations, scientists are generating synthetic data using traditional physics models to simulate the climate of, say, 2050 or 2100 and feeding that into the AI.
Oh, brilliant. So you are artificially exposing the neural network to unprecedented heat. You're giving the autocorrect a future vocabulary so it knows what a 2050 heat wave looks like before it happens.
Exactly. Another highly promising solution is transforming the inputs into what researchers call climate invariant variables.
Okay, what does that mean mechanically? How do you make weather data invariant to climate change?
So instead of feeding the AI raw temperature data like telling it the air is 25 degrees Celsius, you transform the data to focus on the underlying physics that drive the weather.
Like what?
For example, you might train the AI to look purely at the gradient of atmospheric pressure or the velocity of the jet stream. Or you normalize the local temperature by subtracting the global average temperature for that specific year.
Ah,
You're essentially forcing the neural network to understand why the atmosphere is behaving a certain way based on its physical shape,
yeah.
rather than just blindly matching the absolute temperature to a historical record.
You are teaching the AI the rules of the game rather than just letting it memorize the previous score. You want it to understand the fluid dynamics without having to do the slow math of a traditional supercomputer.
That is the ultimate goal. We need to make these AI architectures robust against a changing baseline, because right now, their absolute reliance on historical data is acting as an anchor.
Wow. This deep dive has really taken us through a profound technological blind spot. We have engineered incredibly powerful, lightning-fast AI models to map our future, but because they learn exclusively from history, they are structurally condemned to predict history.
Beautifully said.
We've seen how weather models like ForecastNet fail to see modern extreme heat because it simply didn't exist in their training data. And we've seen how even when you explicitly give a climate model like ACE2 the data on carbon emissions, it still struggles to grasp how rapidly our coldest winters are disappearing.
Leaving our forecasting systems with a 15 to 20-year lag behind reality. It is a sobering reminder that artificial intelligence is ultimately constrained by the world it was trained in.
Yeah.
But this raises an important question, and it's something I want you, the listener, to consider. We have just spent this time analyzing how our most advanced supercomputers are trapped by the climate of 1998, their baseline anchored in the past. But what about us?
What do you mean by that? How does that apply to human intuition?
Well, think about your own internal baseline. How much of our own human intuition, our mental models of what a normal winter feels like, or what constitutes a safe summer day, is also suffering from a 20-year lag?
Oh, wow.
We grew up in a climate that physically no longer exists. When a modern heat wave hits, our brains often tell us it's just a fleeting anomaly, because that is what our historical training data, our childhood memories dictates. Are we, just like the AI, constantly forecasting our own future using yesterday's climate?
Yes.
Are we pulling our own expectations back to a historical mean that is already gone?
That is a haunting thought. We are the neural networks. We are anchoring our expectations to the snowdrifts and summer afternoons of our childhoods, violently regressing to the mean of our own memories while the physical world changes around us.
Exactly.
That is definitely something to mull over the next time you check the forecast.
Yeah.
Thank you for joining us on this deep dive. Stay curious, question your baselines, and we will catch you next time.